Okay, so let's start. Any questions about last lectures or any other lectures? Okay, so we were doing differential amps. For those of you who didn't attend last lecture, I hope you have gone through the video. Okay, so this essentially was a structure that we were looking at, and we saw what are the common mode and the differential mode gains. I also talk briefly about what they mean. When we were at the end of the last lecture, we saw that firstly, what is the common mode gain for this structure? Is 0. And what is the fundamental reason behind that? There was no incremental current, right? When both V1 and V2 move in unison, the current I naught, or rather in this case, if I say 2 I naught, so the quiescent current I naught, which were flowing in both these branches, wouldn't have been affected. If they are not affected, then V01, V02 will not get affected, which means no movement of any voltage. Hence, output is constant. Hence, your common mode gain is 0. However, if what is the, under what condition this assumption is no longer valid? We discussed this at the fag end of the last lecture. Right. So we essentially have assumed that M0 is an ideal current source, right? Which means that we have neglected its output impedance. However, we cannot do that. There is obviously a parasitic. Under this, when we are trying to figure out what is the common mode gain, we cannot do that because we are comparing essentially with 0, right? So we will have a parasitic conductance, GDS. By the way, one caveat, note that it's customary to sometimes not replace the transistors with their incremental model always, because it tends to get cumbersome if you replace this compact transistor model with the full-blown small signal model. So what I will assume is when I am doing incremental analysis, I'll still keep the transistor as is, but we will, at the back of our mind, we will ensure that the symbol and notations will essentially convey the information that whether we are doing incremental or full blown, right? When we are using small notations like small v, small GDS, small GM, we know that we are concentrating on the incremental model, and we will make necessary assumptions that go along incremental model. And when we are trying to figure out the quiescent, we will use the caps, right? So that's the general convention. But however, it's not necessary that you need to follow that. If you are more comfortable with replacing a transistor with their small signal equivalents, feel free to do that. And that's actually a good habit when you are starting off. Okay, so the reason I said that is when I replace this GDS, when I added this, it doesn't mean that you have a explicit resistance to ground. This GDS is an incremental model of the GDS, and I am superimposing the incremental model on this transistor equivalent circuit, right? But the assumption is that when we are using this incremental models, we will use the appropriate notations and appropriate approximations, right? Okay, so now when we have this GDS here, what changes? Vx, right? So this was Vx. Fine. So now find out what will be V. So firstly, to find out common mode gain, you'll have to apply identical incremental inputs at both sides. So if you have V1 and V1 on both sides, so this is, let's say, V1, incrementally V1, this incrementally V1. Find out what is V01 by V1. Find out and tell me. Okay, so there are many ways of going about doing this. So one way is, so firstly, I mean, I saw some of you also included I naught in the calculation, but I naught is quiescent, so constant current source. I naught doesn't really play a picture in the incremental model. So when we are talking about incremental models, we are dealing with GM, GDS, and all those things, right? So the way I would prefer to go about doing this is, if I know the incremental node voltage at this, if I assume the incremental node voltage here to be Vx, then I know this incremental current. How much will that be? Gm times V1 minus Vx. Similarly, this current also I will know, which is identical, and I will know this current also because it is Vx times GDS. So I basically apply KCL at Vx. So if I apply KCL at Vx, what do I get? Twice Gm times V1 minus Vx is equal to Vx times GDS, which means right. So if I know V1 in terms of, if I know Vx in terms of V1, then I know the incremental current, which is Gm times V1 minus Vx. So this incremental current, we call it ICM because we are talking about common mode here. So ICM incrementally will be Gm times V1 minus Vx, which is which means that my V01 is minus ICM times RL, right? Because I am pulling current out. So minus GM times RL. Sorry, I made a mistake. This is 2 GDS. This will be GDS here, right? V1, which means your ACM, mod of that, if you are interested in the magnitude only, is GDS times RL. Okay, so and this kind of matches our sanity check also, because if GDS is 0, which means when it was an ideal current source condition, you will see that ACM was going to 0, right? So so that is a 0th order sanity check that that makes sense. Okay, any questions? Okay, so so this is as far as the common mode gain is concerned. How we saw how the common mode gain is. We are seeing rather how the common mode gain is changing when we are including the parasitic conductance or the channel length modulation conductance due to channel length modulation of the transistor M0. But what happens to the differential gain? Does it change? So let's. I mean, we should redraw this because that circuit is becoming cumbersome.
Sir, can you show the expression once more for ACM? Sir, GDS RL is limitless, and in the denominator it is GM.
Oh yeah, something messed up, right? Where did I mess up some things? Okay, times GM, right? Yeah, I missed this GM, right? Thank you. Yeah, bad mistake. Yeah, cardinal sin. Thanks. And you have this stuff here, so I'm not sketching because that is irrelevant for the purpose of incremental analysis of this diff pair. So when I am planning to do differential gain, I'm applying a differential input as V1 minus V1, and I'm trying to figure out either of the branches, doesn't really matter. What will be V01 by V1? So again, how will you go about doing this? Do the same thing. Do the same thing and tell me. So what will be Vx under this condition? Vx will be 0, right? This, I mean, that is quite evident because this current is Gm times V1 minus Vx. And this current is, rather if I do the other way around, okay, you can do this also. Gm times minus V1 minus Vx. And if you add them up, right? So Gm times V1 minus Vx plus yes, right? So which essentially means that you see that your V1 gets cancelled and you are essentially left with, what are you left with? Minus 2 Gm Vx equal to Vx GDS. And this condition is only satisfied, I mean, this has to be satisfied for any Vx, right? And this can only be satisfied for Vx equal to 0. Or if you want to do this mathematically, this becomes 2 Gm plus GDS times Vx equal to 0. Since this is not 0, Vx has to be 0, right? So, and this is the mathematical way of going about it. And I mean, you can also think about it in this way. It's the fact that when these two, so this Vx, this node was what? This node was essentially an average of V1 and V2, right? So when that is essentially acts as an average of V1 and V2, then when there is no average, right? When the average is 0, that will also be 0 incrementally, right? So, so that kind of makes sense. So this makes life easy for us because if Vx is 0, then this M1, this M1 transistor essentially behaves like our classical common source amplifier where the source is incrementally grounded. And source is grounded in a common source amplifier, not incrementally, absolutely. But in this case, it looks like under the differential mode, the source of M1 is incrementally grounded. So, I mean, whatever results you get for common source amplifier also is essentially the result for a differential mode of operation, right? So V01 by V1 becomes Gm times RL. Okay. Okay, fine. So now let's, by the way, any questions? So that what, yes.
If I find out the current at that Vx node, and if I want to find the voltage, then voltage will be current times impedance of that node.
Okay.
So here two current is coming, which is opposite.
Right.
You can say this voltage is 0.
Two currents, if they are equal and in opposite direction, basically whatever you are pushing into a node, the same amount you are pulling out, then the node will not change, right? So that's what is essentially happening here. So whatever incremental current M1 is trying to push, exactly same amount of current M2 is stealing, right? So nothing needs to go to GDS. Since nothing is going into GDS, your GDS, I mean, Vx is not getting excited. In a common mode sense, if the opposite is happening, both of them are pushing and the current has nowhere else to go but into GDS. So that's why GDS was going up. Rather, Vx was going up, right? So, or rather, that you were seeing incremental current because there was some place for that current to go, right? If GDS was 0, that mean, no current, there was no place for the incremental current to go, which means the only solution was current itself will not be there. So Vx will change accordingly. Okay, fine. So essentially we see that putting, including the effect of the parasitic conductance of M naught has essentially no effect in the incremental differential gain, but has some effect on the incremental common mode gain, right? And the culprit for the common mode gain is essentially GDS. Okay, so what do we need to do if we have to reduce the common mode gain, right? So what I'm trying to get at here is, since we are talking about common mode, let it be V1, V1. So what do I need to do if I have to increase or reduce the common mode gain, right? So now I have GDS here. So the obvious answer is I need to reduce GDS, right? So how do I reduce GDS? Yeah, so one is cascode. I mean, the first order is essentially to say that I will increase the length of M naught, right? So let's say you started off with some length W by L of M naught, and you found that some GDS that you got, but you want to reduce GDS, then what should you do? What is the first order? You can simply increase L, right? But if you increase L, that will not suffice. You'll have to increase W also, right? Because otherwise the quiescent conditions will get affected, right? So if this is M0A and that is M0, so you have to increase both W and L to reduce GDS. But what happens if I keep on increasing W and L? This is slightly, I mean, this is not something I have discussed, so it's not fair for me to ask you to answer this question. So let me volunteer. So what we have not discussed till now is the fact that these transistors, right? These transistors, if you see the cross section of these transistors, if you recall in one of the earlier classes we discussed, this cross section of a transistor essentially looks like this. This is P substrate. This is N doping. You have a oxide here, and on top of that you have some polysilicon. I mean, nowadays we don't use metal, but metal is again making a comeback. But regardless of that, so let's say this is drain, this is source, this is gate. So what? This is a cross-sectional view of that. But if you just rotate it and do look at the 3D view, the 3D view of this is of this gate is essentially so I messed up the color coding, right? So this was supposed to be the gate oxide. And let me use a different color other than this for drain and source. Drain was something like this, source was something like this. So this goes somewhere here, and you have terminal coming out, terminal coming out, terminal coming out. So this is drain, source, this is gate. So when I say this terminal coming out, these are essentially metal lines that you drop on the N plus and the gate. Sorry, I also didn't put a actual gate, right? This is oxide. So the gate should be on top of this. Okay, so in this case, obviously, this is the length because the distance between drain and source is the length, and this is W. Okay, so so as it turns out, the thing that we haven't discussed till now is the fact that there is a capacitance between your gate. Now, obviously, there is a capacitance because Cox is a capacitance, but other than that, there is also a capacitance between your gate and drain and gate and source. There is an overlap part, right? So this, if I zoom in here, so this is, it's not as if wherever your gate ends, the source starts. There has to be an overlap because otherwise you run a chance of missing missing any overlap, right? So there will be an overlap. So because of this overlap, let's concentrate on the drain side. Because of this overlap, there will be a capacitance between gate and drain, right? So, and that capacitance is this, we call it CGD. So let me call this CGD gap. So this is CGD. This CGD is proportional to, obviously you see the CGD is proportional to the width of the MOSFET, right? So as you keep on increasing W, assuming that the overlap here at this junction remains the same, CGD is obviously proportional to W. So when you keep on increasing W and L, right? When you, in order to reduce GDS, you are increasing L, but in order to keep W by L same, you have to increase W. So what is happening is you are inherently saying that even though you are not directly intending to do that, but this capacitance CGD is increasing. Okay. Also, there is a capacitance between drain and body, right? Because what is this? This is an N plus. This is the N plus doping, and what? So this is an N plus doping, and what is this? This is a P minus substrate. So you have essentially this is a PN junction, right? So when you have a PN junction and it's a reverse bias PN junction, obviously otherwise, transistor action is lost. So in a reverse bias PN junction, so you will have depletion region, and because of that, you will also have a capacitance between the drain and body, right? So CDB, which essentially means that CDB, that is the capacitance between the drain and body, is proportional to what? Is proportional to also W, right? And W, and one might say this, whatever is the junction, whatever is the amount of doping you have to put to get at least a junction going, right? So, so that is not particularly in your control. That is given by the process technology guide. The fabrication maybe TSMC or Global Foundry or whoever is making the transistor will ensure that there is certain amount of distance that is required to get a proper doping of N plus. So that is not in your control, but in your control is what? W is in your control. So I can say that CDB is also proportional to W, right? So when you increase W, both CGD and CDB will start increasing. So if I now, let's not consider CGD for the time being, let's only concentrate on CDB for the time being. So if CDB keeps on increasing, right? So now you, in your mind, at the back of your head, you assume that V1 has some frequency component. It's not DC, right? If V1 has some frequency component, as the frequency increases, rather in that when you are trying to operate this differential amplifier with relatively higher frequency, then what is the effect of this CDB? It becomes lower and lower impedance, right? So at frequencies where the impedance due to CDB will become comparable to GDS, then the current, the common mode current will prefer the path through CDB and not GDS, right? So at frequencies, so if at omega naught CDV becomes greater than GDS, right? So your impedance looking down, right? So let me call it G tail. So another jargon, this transistor M0 is called a tail transistor. So if I call it G tail, G will start becoming approximately equal to, or mod of this will start becoming approximately equal to omega naught CDB, right? So now you run into problem because now you don't have any more handle, right? Because you want, so what will essentially happen is in this expression, your GDS gets replaced by omega naught CDB. Okay. So which essentially, or rather J omega naught CDB, if you want to be more accurate, which means that you cannot anymore, I mean, by simply increasing W and L, you lose your handle of reducing common mode gain, right? It's no longer dependent on GDS, right? So whole purpose of increasing length was to reduce GDS, but you can play the game only so much because after certain frequency or after certain cutoff of after certain value of L, your ACM is no longer dependent on GDS. Okay, so which means we'll have to look for other solutions, right? So increasing. So by the way, this is a typical problem of trying to increase your output impedance or reducing GDS by increasing L. So you'll have to see in cases where this is not a problem, you can keep on increasing L, but in scenarios where maybe you are dealing with a moderately higher frequency or maybe even some low frequencies where if you make W by L so large that the capacitance starts coming into picture, then you have to be careful that maybe I can't play that game all the time. Okay. Okay, fine. So let's say I have maxed out. I cannot increase L anymore, right? So what is the next way of increasing output impedance? Now let me simplify it further. So what I'm essentially saying is that now we are only bothered about increasing the GDS of this, right? Or rather increasing the R out of this, right? So we have a different diff pair here, but as we saw, ACM is mostly dependent on the output conductance of the tail transistor. So diff pair is as is. I mean, I can break the problem down. I say that diff pair is not a problem anymore. So I'll concentrate on just simply increasing the R out of the tail transistor. So one way we saw is I can keep on increasing W and L, but we run into trouble. So then what else can we do? What are the other ways of increasing the output impedance of looking into the drain of anything? I mean, we have done it. Okay, so yeah, so let me take one at a time. I'll come to cascode later. One was degenerate, right? So how do you degenerate? Resistance at the source, right? Okay, so resistance at the source. You put a resistance at the source. So now note that there is one more requirement of our current source, right? So if this is 2I0, I want this also to be 2I0. I do not want the bias conditions to get changed. But now will the bias condition get changed? It will, right? Because the VGS of M0A and VGS of M0 are not same. The gate are same, but obviously when you put a resistance at the source of M0, there will be some current into the resistance. The source of M0 will not be grounded, which means this will not have this 2I0. So now, which means this is not useful, but this idea is useful, right? What is it that we are trying to do? We are trying to get an architecture which is of this form, because when I look into the output, when I look into the drain, what is the approximate output impedance? Yeah. Right. So if I call this GM naught, because now we are having many GMs. Right? So if this is R, so this is essentially approximately equal to GM naught by GDS naught times R. Right. So go back to your initial small signal assignments. So which means that we can do something like this, but not in the form of just simply adding a resistance at the source of M0, right? So what I mean, how can I? What are the other ways of going about doing this?
It's a simple current source at the top of the.
If you have a, but that this terminal, you have to recognize that this terminal is connected to diff pair, right? You cannot have a current source directly there, right? So what are we trying to do? We are trying to say that I mean, this R, think of this R as this R, this RDS. I want to increase that RDS. So what can I do?
So you can put another transistor on top of
Right. So essentially this, if I know that if I put another transistor on top of R, the effective impedance now gets amped up by the gain of the top transistor, right? So I can simply do this, right? And if I call this as GM, now I have to use some other names, right? Maybe MC. So GMC, GDSC. So which means that the impedance looking here will be RDS times GMC by GDSC. Right? So as long as your GMC over GDSC is more than 1, you get higher RDS, right? But I have to see how to bias this in saturation, right? Something seems confusing. So if you can tell me what is confusing you, I can address that. Which part is confusing is, I mean, are you not convinced that this is the output impedance? Or are you not convinced that this output impedance will increase? What part is confusing? Or are you convinced? You're convinced. Okay, fine. Fine. So now let's deal with this, because just simply putting a transistor on top will doesn't really serve the purpose as long as we haven't addressed the biasing. So note that we have done all these things in incremental sense, right? All these are incremental pictures, which means that under the hood, we are assuming that we have been able to bias. Now we have to see that how we can actually go about biasing it. Okay, forget about this node. I mean, we can assume that node to be some constant voltage also, it doesn't really matter. So this is M0A, this is M0, this is MC. So how do I ensure that what will be the voltage, let's say VC? What is the minimum VC voltage to ensure that M0, MC, M0A, all transistors remain in saturation?
VDS 0 plus threshold voltage.
V over time of M0 plus VGS of MC. Is equals to.
Okay, I am confused. So, okay. So I don't want the answer directly. So tell me the thought process of how will you go about figuring this out?
So we need to see the like overtime voltage of both the transistor. That should be minimum like V over time. I mean the VDS should be minimum like V over time for both the transistors.
Okay. Okay. So let's start from somewhere. Where do you want to start?
So M0.
Okay. So what do you want to do with M0?
VGS minus VTH.
Okay, so your M naught will have some. So what is the VGS of M naught? So VG.
VGS is VTH plus
Threshold voltage under root 4 I naught mu C of W over L of M naught. Right? So this is V over drive. Right? So minimum voltage of this node has to be V over drive. Okay, so then what has to be the minimum voltage of VC? Assume that M naught and MC are sized identically, both are W by L, same W by L for ease of calculation. So if this is V over drive, what should be VC min? Only one threshold?
To maintain the current, VGS.
You need to have the same VGS, right? One threshold plus V over drive. The threshold is really turning it on. In order to support that current, you need V over drive also. I mean, only turning the tap on is not sufficient. You need to have adequate force in water.
And the VC minus V over drive, that should be equal to the overdrive of MC. Is that?
Okay, so let's see. So your VC main, I mean, once you know this V over drive, your VC main has to be this V over drive plus VGS, right? So which means this has to be VGS is what? 1 V over drive plus threshold voltage, right? So 2 V over drive plus threshold voltage, right? So and this, assuming your V over drive is whatever we mentioned here, right? So this has to be VC main to keep everything in saturation. Do you agree? Okay, fine. So let's assume we have done this. So our output impedance looking from here will be higher than GDS, higher than 1 over GDS, right? Our conductance will be lower than GDS, no issues. But do you see any issues with the actual mirroring of the current of 2 I naught? Now I'm not talking about only first order assumption of keeping VGS same. Take into account the fact that the currents of 2 transistors are also dependent on, to a second order, VDS also, right? So in order to ensure that two transistors have identical currents, you need to have VGS same and VDS same, right? If you keep VGS same to the first order, obviously currents will match to some extent. But if I want really highly accurate current mirroring, right, or current matching between 2 branches, I also need to ensure that the transistors have same VDS. Okay, so with that taking that into perspective, can you tell me whether these 2 branches will have same current? Yes, somebody from here. Is the question clear? So repeat, tell me the question. What is the question? Yeah, tell me which VDS will it depend on, right? So let's assume this is interested. This is I M naught A, and I want I M naught. So VGS of these 2 transistors are same because directly connected. But VDS is not same because it's being set by something else, right? So now since the VDS is not same, clearly the currents will not be same. I mean, as I said, I mean, to the first 0th order, currents will be same if you neglect VDS. But if you start to get into more and more accurate matching of currents, then you have to take those orders into those things into account also, which means you need to keep VDS same also. So clearly VDS in M0A is equal to VGS because it's diode connected. So this, but your VDS of M naught is V over drive. So these 2 voltages are not equal, right? So this voltage and these voltages are not equal. These are not equal, which means that the current I M naught A and I M naught will not be identical. So which means that I have to ensure that they are also identical somehow. Okay, so how do I go about figuring that out? So at this stage, forget about the fact that you have to keep VC to be VC min. VC can go up also if it's required.
To make the V overdrives would be controlled by this node.
Yeah, so let's say, let me call it VD0. So you have, as you said, you have to ensure that your VD0 is equal to this voltage, right? If you can ensure that VD0 is equal to the drain voltage of M0A, then both the gate and the drain voltage of M0 and M0A will be same, and then your current will be mirrored properly. So how can I do that?
Sir, in this case, we cannot connect this DAC connected working not, right, sir?
You mean I connect here?
We cannot do that, right?
Yeah, obviously you cannot do that, right? Yeah. Yes. So how can I make sure that VD naught is equal to VGS? What is my, let's say I don't change the configuration, I still have this MC on top. What is my handle to change VD naught? Let's not change WIL. Keep WIL same. And there is only one thing we can change, right? What is that? VC, right? So what, I mean, now your V overdrive is lesser than VG, or VD naught is lesser than VG under this, whatever we have done till now, or higher than VG? It's less than VG, right? Because VG is this quantity, VG is this quantity, and V overdrive is this quantity. So obviously your V overdrive is less than VG, right? So, so which means that I have to increase this VD naught voltage to have proper current matching, right? So if I have to increase VD naught, what can I do?
Increase the current of the
So VC we can change by increasing the VC. The current will increase.
Okay, I will come back to that. But you said something increase the current. Which current?
Current through MC.
How will you affect the current through MC?
If you change the VC, then current will increase, then that VD will increase.
Okay. So, okay, but yeah, what I understand what you're trying to get, but that's not the correct way of thinking. I'll come back to that why. Anybody else?
Difference of 1 VTH.
Correct, 1 VTH difference, yes.
So if we increase VC, VOD, VD naught should increase, right?
Yeah. So what he is saying is that if you increase VC, VD naught should increase. If I want to argue that why should it increase, why cannot VD naught remain the same?
If current through M0 is fixed,
Yeah.
then only it will increase.
Yeah, so if current through M0 is fixed, to the first order, we are planning to do that, right? Essentially current mirror, right? So it's supposed to be constant current. So if current through M0 is fixed, then the VGS of MC will be fixed, right? So if VGS of MC is fixed, if I yank the gate, the source also has to yank similarly, right? So which essentially means that if I increase this, this voltage will increase and vice versa. Right, so VGS of, who is setting the current in this right hand side branch? Is MC setting the current or M0 setting the current? M0 is setting the current. The primary, I mean, we are trying to now fix the second order effects, but the primary first order effects is current is being set by VGS, right? That is always true. So the first order, to the first order, the current in the second stack on the right hand stack is being controlled by M0. Right? You change MC, you change something on MC, maybe the current will change by small amount, but it's primarily, it's not setting the current. So I can, to the first order approximation, I can think of, I can assume that the VGS of MC is constant. But now I want to increase VD naught, which means that I can increase VC, right? Is the logic correct? See, I have made multiple approximations here. What approximation I have made? One approximation I have made is, while calculate, we want to ensure that my second order effects are also taken into account, but I have not taken the second order effect of MC into account. You understand what I'm trying to say? I am saying that if I increase VC, while trying to figure out how the VGS of MC is changing or not changing, I am assuming that your current in the right hand stack is constant, right? So what I'm okay, so maybe this might sound confusing if I don't write it down. So what equation am I dealing with? I am trying to deal with this equation of a transistor now. And I am saying that I will ensure that VDS of M0A and M0 are same. Correct. But you might notice that while talking about all these arguments of how the VGS of MC is changing, I have not taken VDS of MC into account, because what I am doing, I am saying IDS of MC is equal to mu Cox W by 2L VGS of MC minus threshold voltage whole square. I have neglected this additional term for MC. Right? Because it is only then your VGS is constant, right? Otherwise, I'll end up with multiple equations of third order and all those things, right? So why is this approximation valid on MC and not on M0?
Because current is generally driven by M0.
Exactly. So the current is being set by M0. So if you can do this exercise yourself. Don't neglect anything. Just use this 1 plus lambda VDS term for both M0 and MC, right? And see, what answer you come up with, right? In terms of the effect of VC on VD0. So you will see, obviously, we'll end up with third order equations, at least second order equations, and so on, right? So the algebra will become messy, but the intuition or the crux of the operation of the circuit you will lose. The reason I am saying is that, as you pointed out, the current in the stack is being set by M0. So if the current in the stack is being set by M0, then I can neglect the second order effects in the other transistors, right? So if I already know that changing VC by, let's say, delta V changes VD0 by approximately delta V, right? So that change itself, the VGS change itself is almost 0, which means that changing VGS, changing VC doesn't even change the VGS of MC, which means that changing the main control knob doesn't really change the current. The primary knob itself is not changing the current. How will the secondary knob affect us? VDS is a secondary knob, right? So that's why I can neglect the effect of the secondary knob on MC. Okay, but I don't want to neglect the secondary knob on M0, because that's what we are trying to match. So that's why I have neglected this stuff for MC, and we are saying that, okay, maybe the channel length modulation is not much of an issue for MC. Okay, so now if that is the case, so I want to know, so this is VG. I want to make this also equal to, let me call this VGS, because that's what typically we are trying to address. So I want this voltage VD0 to be also equal to VGS of M0. Correct? So if this has to be equal to VGS of M0, what should this voltage be? VC should be equal to?
need not use the VGS of MC.
Right? So twice, I mean, basically I have to add one VGS. Correct. So I have to add this VGS, right? So this will become twice VGS of M0. Okay. So now the question becomes, how do I manufacture this twice VGS of M0?
If we put a same transistor on top of this MOA.
Yeah, right. So how do you manufacture a VGS? Diode connected, right? So how do you manufacture twice VGS? By keeping two, right? So if you push I0 here, this becomes VGS. If I have another one, then this becomes twice VGS, right? Same current. So I can have this stack and then connect this VGS here. But I mean, I don't want to do that because I already have I0 and one diode connected transistor on the left stack. Like what I can simply do. Do this, right? Okay, make sense? Okay, fine. So this seems to address our problem of having accurate matching between both sides in terms of current, and also increasing the output impedance looking from the top. Right? So, but there is one more issue with this. The issue is, what is the minimum voltage now at this node? What is the minimum voltage now at this node that is required to ensure that both transistors, this MC and M0, are in saturation? No. Your gate voltage of MC is twice VGS. So this minimum at Vx, this is Vx, right? Note that it was connected there. So Vx minimum is twice VGS minus threshold voltage. One VGS minus threshold voltage is essentially an overdrive. So VGS plus V overdrive.
Overdrive is not same for both the transistors.
I have assumed same W/L everywhere. So it will be same. Right. So obviously you can play around with W/L to change overdrives, but to the first order, they are same. Right. But note that if I go back, okay, if I have to go back to the previous lecture, what was the minimum Vx required to keep the tail transistor in saturation? V overdrive of M0, right? So if that had to be V overdrive of M0, now I want to keep VGS plus V overdrive, right? So I am eating away some voltage headroom. So what will this directly affect us in terms of ICMR? What will the common mode range will get affected, right? What will be the minimum absolute voltage of on the gate of M1, M2? So this is something that we discussed in the last class. At least the folks who attended the last class should be able to answer this. So this voltage is being set by whom? Quiescent voltage at Vx is being set by which transistors? M1, M2, and which voltages? VB, right? So the quiescent voltage of VB, quiescent voltage of M1, M2. So if the minimum requirement of Vx has increased, the minimum requirement of VB will also increase. So how low you can go with respect to VB gets compromised. That is essentially ICMR minus, right? Your ICMR minus gets compromised. So So and this compromise in this case, especially in low voltage process, can be significant, because let's assume you are working with a 1 volt process, right? Nowadays 65 nanometer, lower 28 nanometer, those are all typical voltage ranges. VDD is 1 volt, 1.1 volt, something like that. Yes.
And we were comparing, we are eating away 1 VTH. We were comparing.
We were comparing with the case with where we didn't have the cascode, right? So this is the classic diff pair with no cascode. We are trying to put a cascode here to increase the RDS, but that is coming at the cost of a VGS, extra VGS, right? So what I'm trying to get at here is that if you have, let's say, a threshold, you are operating with a transistor with operating in a process with VDD of 1 volt, 1.1 volt, your VGS still is of the order of 400 millivolt or 300 millivolt. Your threshold voltage is your overdrive, you let's say keep 100 millivolt. So which means the threshold voltage is, your overdrive is 100 millivolt, your VGS is 400 millivolts. 500 millivolt itself goes in biasing your tail transistor. Half of your supply has gone just to bias your tail transistor. So that's that is something obviously you cannot use. Okay. When supplies used to be like 5 volt and all, yeah, sure, why not? But nowadays this is almost a no-no. So we'll have to do something about this. So what is the something that we would want to do? So we still want to retain the cascode, but with this cascode, let's assume that everything is biased properly and all. So what is the minimum voltage at this node that I can operate with when I still have M0 and MC both in saturation? From the reason I'm asking is, if I know the minimum voltage, then I can back calculate and figure out what is the minimum voltage here, right? So what is the minimum voltage of MC that is required to keep both MC and M0 in saturation, regardless of the fact that I can, let's assume we can figure out what this VC is supposed to be.
Overdrive voltage of
2 overdrive, right? So 2 overdrive, one V overdrive and 1 V overdrive. So this is the minimum that you can go. So Vx min is equal to 2 V overdrive. This is not obviously as good as one V overdrive, but if you assume V overdrive is like 100 millivolt, maybe 2 V overdrive is 200 millivolt. It is much better than 500 millivolt, right? 1 VGS plus is much better than 1 VGS plus V overdrive. So this is the best we can do, and this is what we should be able to target. Okay. So now the question is, if we have this, if we want this, what is the voltage that you want at VC? Yes.
Sir, if we bias at this 2 overdrive, in that case, suppose the VB is reducing. In that case, VX will.
Yeah. Go ahead.
Is one of the
It will. See, so you can only get V overdrive if you have one transistor. Right? Moment you put cascode, you are losing. But how much are you losing? If you use the previous biasing scheme like this, you are losing 1 V overdrive plus 1 VGS. So that is quite bad. So we don't want to do that. We want to see what is the next best thing. I cannot get V overdrive using cascode, definitely. So maybe the next best thing is twice V overdrive.
That will create problem.
It will create, to some extent it will.
It is at the edge, right?
Yeah, your VB min, that ICMR minus will still get compromised, but not as much. Okay.
Sir, actually, my doubt is, suppose the Vx is 2 VOD. Now, if I reduce the gate voltage from M1 or M2, so Vx is reduced.
Right.
And as soon as slightly reduces, because it is at the edge.
Yeah, so you don't bias at the edge. You never bias. As the ICMR minus is the limit. You never bias at the edge of anything, right? You bias with some margin. So, I mean, essentially, these courses are to give you an estimate of the limits. Where you bias is a design philosophy, right? So that is more of a requirement specific thing, right? So you never bias at the limit.
So sir, we'll basically try to find the VC minimum for this case, because
Correct.
VC is basically manipulating the
Correct.
that voltage.
So what is the VC minimum required? One threshold voltage above this, right? Right. So VC min has to be equal to 2V over drive plus threshold voltage, right? So if I rewrite this in this form, one threshold voltage plus twice, sorry, 2V over drive is, this becomes 4 if I take it inside the bracket, times that it was 2I0 we were dealing with, right? Mu C ox W by L. So how can I manufacture this voltage? This seems to be of the form of some VGS, right? Threshold voltage plus some under root term, right? So I should be able to generate it using some diode connected transistor. So what current, what W by L? Yeah, 4I0 current, same W by L should give you this, right? So if you have 4I0 current, same W by L should give you this voltage. So you can connect it here, you will get VC min. Alternatively, I can say that this 4, I can bring it down. I can say it's similar to 1I0 and W by 4L. Right? Essentially the same thing. So obviously I would prefer the latter because for biasing, I don't want to consume too much power, right? Yes. Oh, sorry. Yeah, right. This is 2I0. Yeah, thank you. So these were all 2I0s. Okay, so this is how I can control VC, but we land up again in the same problem that these two voltages are not same. Right, so which means again the accuracy of mirroring will not be as good. So now I want to do this. I don't want to have VGS plus 2V over drive. I want to have VC to the voltage that I am showing, but I also want accurate matching. Right, we are getting greedy, right? So we want accurate matching, and also we don't want to get into this extra VGS problem. So what can I do? So obviously I cannot diode connect here, right? If I diode connect here, you will have a problem. Because if you diode connect here, then you have to ensure you have VGS here at the equivalent to VGS there. So I cannot diode connect there. So I have to do something. What is that something? Any thoughts? So see, ultimately the issue is I need to draw a parallel between these, right? So the left branch and the right branch. I need some sort of diode connection in this branch, but I need to ensure these two voltages are also same, right? And how do you ensure this voltage is same as that? Typically, how do you ensure? You will have to, I mean, you cannot simply fix a voltage there, right? It has to be done by a cascode, or rather it has to be done by in some MOSFET way. So how do you, I mean, what is the MOSFET way? I mean, how did we fix this voltage here? We put a cascode on top We put a cascode transistor on top and we said that this voltage VD0 was being set by this voltage VC, which means I need to have a similar arrangement on the left branch also, right? So if I want these two voltages to be same, I need to have a similar arrangement on the left branch also. Otherwise, I will not be able to make them same, right? So at the bare minimum, we should have that arrangement. Now, how do I figure out how to do a diode connection? That we'll see. But at least we should have this. So let's put it through. Let's put it here. And this VC is getting generated by this 2I0 W by 4 by L. So that we already know. So I'm not connected here also. Okay. So now I have a 2I0 current source, and I need to bias this stack in such a way that this 2I0 current gets absorbed, right? I cannot simply connect 2I0 here. What happens if I connect 2I0 this here? There is no feedback, right? So it is equivalent to saying that we have a current source 2I0. I want a transistor. I want this 2I0 to flow through this transistor without affecting its saturation region operation. Then what did we do? What was the argument? The argument was if I connect this and observe this node, if this node voltage increases, I need to increase the gate. If this node voltage decreases, I need to decrease the gate. So we simply connected it here. So now we don't have this particular arrangement. The arrangement that we have is this. This is some constant voltage VC. This is still my control voltage, right? So if I connect these two, and I observe this node voltage, what happens if this node voltage increases? What information am I getting? If this node voltage increases, what information am I getting? And let's compare this 2I0 with ID. 2I0 is greater than ID, which means that what should I do? I need to increase the VGS of this is M0. So this is M0A, right? And let's see, this is MCA. So I need to increase the VGS of which transistor? Why not the upper? Why not the MCA?
The actual current is fixed by the loss.
Yeah, right. So as you said, I mean, the current in this stack will be controlled by the VGS of M0A, and VGS of MCA will be set by that. You cannot independently change the VGS of MCA because source is not in your control, right? So if I have to now, if I observe this intermediate voltage here, and I see that voltage is increasing, which means that I have to increase M0A voltage, right? So I can simply do that by connecting it here, right? We have not yet established whether everything is in saturation, but we'll see. Okay, so this is equivalent to saying I can connect this. I can connect these nodes. Okay, so what is this node voltage? VGS of M0A, which is threshold voltage plus V over drive, which means this node voltage is threshold voltage plus V over drive. Okay, what was VC? VTH plus 2V over drive, right? Is that correct? Yeah. So now, do you think VC, this transistor MCA is in saturation? What is the difference between drain and gate of MCA? 1 overdrive voltage, right? So this is in saturation. Agreed? What about M0A? This is in saturation by default because that's how we have designed it. We have designed it these two voltages to be equal, right? And we also know, we also built it in such a way that M0 is supposed to be in saturation, which means M0A will also be in saturation, right? So using this arrangement, what we have been able to do, we have been able to keep all transistors in saturation. We have been able to implement cascode to increase output impedance. And we also have been able to ensure that the minimum voltage at Vx node is twice V overdrive, right? So this seems to be the best of both worlds as far as we can do with using cascodes and all. And that's why this is called a wide swing current mirror. Okay. VC is here, right? VC, you are. So that is why this particular configuration is called wide swing current mirror. Okay. Any questions before we close?
So with this configuration, we are allowing the Vx voltage to swing very large range, right?
Yeah, larger than diode connections, but yeah, but no, obviously not as large as if we had only one transistor, right?
And it goes minimum to 2 overdrive.
Correct. Yes.
When we are saying that we are keeping the VGS same and VDS same, we are saying that WL should be same.
Yes, that's the assumption. Yes.
Means, can't we forget about VDS and manage with tune with WL?
Okay. Yeah, that's actually also a good question. So, okay. So what he is essentially saying is, forget about all these things. So my current equation is mu Cox W by L, some V overdrive squared times 1 plus lambda VDS. So if this VDS is different, then I am saying that there is some mismatch. I can as well tune this W by L to compensate for that VDS mismatch, right? Yes, mathematically you can do, but there are some problems, some practical problems. One of the practical problem is when you want to make these currents, okay, one very important practical problem is this current, when you lay out these transistors, right? When you lay out these transistors in an IC, something similar to these, so you have to ensure that the mirrored transistors, this M0A and M0 are identical. But you cannot make them actually identical because they are physically different, located physically at different locations. So which means that best you can do is keep them very close. So that is one thing, that you have to keep them very close, and it is not only sufficient to keep them very close, you have to ensure that their aspect ratios are also same. Because, so this is again, these are part of some advanced courses, but so what happens is, if you keep, you can think of these M0 and M0 to be made of some unit cells, some unit transistor cells. If those unit transistor cells are identical, then one copy, if you know that what is the characteristics of one copy, you know that whatever will happen to the other copies are also same. Okay, if something bad happens to this copy, other copy, similar bad things will happen to all the other copies also. Which means that this mirroring will not get affected, because this mirroring is dependent on the ratio, not an absolute characteristics. Okay, so now what essentially will happen is that what you are saying is, if I change this W by L slightly to adjust that for that VDS, I am not keeping all the other branches to be identical in aspect ratio. So their second order effects will not be same. That is number one. Number two is, your VDS is not constant. If you change VB, your VDS will move up and down. That is an even bigger problem. Then you cannot on the fly change your W by L. Right? So that's why you don't do that. I mean, this type of changing, but mathematically, sure. I mean, it's evident, right? I can obviously find a solution of different W by L for which the current matches, but practically you cannot do that because of those requirements. So what he is saying is, so what I'm saying is this VDS has a time dependence because your signal will change, but W by L doesn't. Right? So you cannot change W by L with time to make sure that you are compensating for VDS. Right? Yeah.